This is the universe in a box. Dark matter, supermassive black holes, galaxies, stars, magnetic fields, our universe trapped in a cube. Well, some of it anyway. What this really is our most advanced simulation of the universe and its evolution ever. This very impressive feat is the result of a project called Illustris, the next generation, or IllustrisTNG, so named because it follows in the footsteps of its predecessor, simply called Illustris. It's a collection of state-of-the-art cosmological galaxy formation simulations, and is a computational collaboration involving theoretical physicists, astrophysicists, scientists from the Max Planck Institutes for Astronomy and Astrophysics, Harvard, MIT, and more. And it presents a solution to a long-standing problem. Observing galaxies through telescopes only lets us see certain properties of those galaxies. Existing simulations have made us choose between two options: large swaths of the universe simulated in low detail, or highly detailed simulations but only of small pockets of the universe. The TNG project allows for unparalleled detail on huge scales, and there are three versions to choose from: TNG 50, TNG 100, and TNG 300. Each number refers to how many megaparsecs long the side of the simulated cube is. So on TNG 50, the smallest simulation, that's a sample of the universe with just, about 230 million light years of space represented per side. To get a sense of what that scale might be like, picture 100 Milky Ways being simulated at once. Just one of those galaxies has a total mass of around 10 to the 14 solar masses, all simulated at higher resolution than has ever been achieved before. TNG 50 lets researchers look at individual phenomena in more detail, while the larger TNG 300 lets us see a bigger range of diverse phenomena, and TNG 100 is the happy medium. IllustrisTNG as a whole is designed to be run on massively parallel supercomputing systems. And parallel computing is a really interesting way of designing both a computer system and the problem that you give that computer to increase computing power. See, in a non-parallel system, the whole computer is trying to solve the whole problem at once, and it has to do it in sequence, as in solve one part of the problem before it can proceed to the next part, and so on. But in a parallel system, the problem is divided into discrete parts that can be solved at the same time. So as you can imagine, for hugely complex jobs like simulating the behavior and evolution of our universe, parallel computing gets the job done just a little bit faster. But even using a parallel system, it took 16,000 processors working 24/7 for over a year to produce the smallest simulation, TNG 50. This was done on the High Performance Computing Center, Stuttgart, in Germany. It's actually one of the most demanding astrophysical computations ever completed, a calculation that would have taken about 15,000 years on a single processor. So a parallel strategy is required for the massive calculations involved in IllustrisTNG. The simulation project takes knowns about the universe, like gravitational force and how it may act on certain materials, the behaviors of those materials under extreme conditions, lots and lots of math and physics that we're familiar with from observational data and experiments and other simulations, and it compiles all of that into a 3D cube full of galaxies. The researchers can take all of these galaxies and look at how they may have changed over time, and the project provides particular insight into the role of dark matter in the evolution of the universe. This is especially important because we're pretty sure that dark matter and dark energy exist and make up most of our universe, but we're not really sure what form either of those things comes in. Like, is dark matter the collective mass of supermassive black holes? Is it a particle? We're still not sure, and scientists are actively looking for it in all kinds of ways. So the hope is that simulations like this will give us far more insight into how dark matter might behave, and therefore bring us one step closer to discovering what it actually is. So researchers are already using this data to understand more about our universe. One scientist was able to use it to demonstrate that black holes play a role in star-forming galaxies as those galaxies shift from their young blue stage to their old red stage. Another team has been using it to study the large-scale magnetic fields that we see all over our universe, where they might come from, how they behave, and how they may influence galaxy evolution. IllustrisTNG plans to continue developing even faster, bigger, higher resolution simulations that let us look at our universe in a box. And maybe the coolest part, all of this data will be publicly available. You and I can just look up the most stunning details of our universe anytime we feel like it. How stellar is that? To learn more about the state of our universe just after it was born, check out this video here, and make sure you subscribe to Seeker to stay up to date with all of your galactic exploration news. As always, thanks for watching, and I'll see you next time.